So I'd mentioned before how when you build your molecular models, most of the model kits look like this. And I mentioned that the bonds here between this hydrogen and the carbon aren't exactly representative of what's going on because this represents the nucleus of the carbon atom and this represents the nucleus of the hydrogen atom. But the truth of the matter is they're really spheres kind of smushed together. So there's another type of model kit called space filling models. Now, I don't recommend you buy them because they tend to be rather expensive, but this is a space filling model of the same thing. Here's a methyl group, a CH3 with what we call the ball and stick model system, and here is a methyl group in space filling where the carbon is the black ball here, and then the hydrogens are the white ones there. And you can see that there are similarities, yes, but there's definitely a difference with our space filling model, and this is what molecules really look like. So when you build a butane molecule, with our normal butane molecule, we had this guy here, CH3, CH2, CH2, CH3, and we noted how you can turn these, and no matter what, it didn't look like those two hydrogens came together. They're still a decent distance apart. You can still get rotation and everything here, no problem. But then if you make butane doing the space filling models, what you find is this. So here is my regular model. Here is butane in the same conformation using the space filling model. Now I'm going to rotate this bond. So these two are like this. Now when I do the same with the butane and rotate it, look how these two hydrogens, right here and here, these two hydrogens actually smack into each other. When I put them down like that, you can see that they run into each other. I can't even get this exact configuration. They run into each other. With this molecule up here, rotating, they slide right by each other, no problem. With space filling, they can't slide by each other without one of them also turning the other one. If this one is turning, this one kind of has to turn with it if they're in this orientation. But if they were in this orientation like this, they cannot go by each other without one of them turning. So that is our steric hindrance. There is just not much room in there. And they will smack into each other with this rotation of this butane, and that's what causes a little higher energy rotation in a butane compared to a normal carbon-carbon single bond. We also looked at cyclohexane, and here is the space filling model of a cyclohexane. And you can see the hole in the middle of this model. Here is how big the hole is. It's just right in here. This is the hole in the middle of a cyclohexane. That's the real size. Note that the size of the hole in the middle of the cyclohexane is much smaller than even a hydrogen. So that hole in the middle of cyclohexane is extremely small. You cannot fit another atom through the middle of a cyclohexane ring. It just won't fit. So this is cyclohexane, and note when you have this model, here it is in the chair conformation. You can see our axial hydrogens up here and the axial down and the equatorial around the outside. Just for reference, here is a tert-butyl group, and note the size of a tert-butyl group compared to the size of a cyclohexane. They are fairly similar in size. There's not that huge of a difference between the size of a cyclohexane and the size of a tert-butyl group. And if you want to put a tert-butyl group on the cyclohexane, it will go equatorial and can spin. There's a little bit of steric hindrance. You've got to orient the molecule correctly to get rid of that steric hindrance, but it can spin. However, it's impossible to fit the cyclohexane, or excuse me, the tert-butyl group axial. I note all this running in, these two methyl groups are running in to the molecule. I can't actually even get it to connect in the axial position using these space-filling models. Just way too much steric hindrance. So this is the space-filling models. This is a more accurate representation of what the molecules look like. But note, they're very difficult to see what's going on. If I said, okay, check out this butane, can you see that that is butane? It's just not exactly obvious. Maybe if I put it in this conformation, you can kind of see it's butane, but it's not the most obvious thing, whereas when I use the ball and stick, oh, it's obvious. You can see all four carbons easily. You can see all the hydrogens very easily. So we tend to use these ball and stick models much more than we use the space filling for when we're demonstrating things, because it's just easier to see what's going on with the ball and stick. Just realize that reality is this. This is the reality of what molecules look like.